The formation of temporary radiation belts around Earth, as observed in May 2024, presents a unique opportunity to study the dynamics of Earth's magnetic environment. This research focuses on understanding the impact of solar storms on the creation and longevity of these belts. Solar storms can significantly alter Earth's radiation belts by injecting high-energy particles into the magnetosphere. The Van Allen belts, composed of electrons and protons, are affected by solar wind and geomagnetic storms. Temporary belts have been detected before, but the May 2024 event was notable for the longevity and composition of the belts. We aim to answer several research questions. How do solar storms influence the formation of temporary radiation belts? What factors contribute to the longevity of these belts? How do the compositions of electrons and protons in these belts compare to previous observations? For our methodology, we will begin with data collection. We will utilize data from NASA's Colorado Inner Radiation Belt Experiment satellite to analyze particle fluxes and belt structures. Additionally, we will collect data on solar wind speed, density, and magnetic field orientation from solar wind monitors. In terms of data analysis, we will conduct a temporal analysis to examine the evolution of radiation belts over time, focusing on changes in particle flux and belt structure. We will also investigate correlations between solar wind parameters and radiation belt dynamics to understand the impact of solar storms. Our modeling approach will include numerical simulations to simulate the effects of solar wind on radiation belt formation and decay, incorporating factors like geomagnetic storms and solar wind drivers. We expect to clarify how solar storms create and sustain temporary radiation belts, identify key factors contributing to the prolonged existence of these belts, and compare the electron and proton compositions of these belts with previous observations to understand their unique characteristics. The implications of this research include informing strategies for protecting spacecraft from radiation hazards during solar storms and enhancing our understanding of Earth's magnetic environment and its response to solar activity.